Hello. In an earlier video on the Raspberry Pi Pico, I said I'd been unsuccessful with getting I2C working. This was because I was trying to use the Raspberry Pi as a primary controlling device, communicating with the Raspberry Pi Pico as a peripheral device. Well, I've now got that working, and I've done the same for the Arduino. In this video, I'll go through both examples using Python on the Raspberry Pi to communicate with C code on the Pico and the Arduino. I won't be using MicroPython on the Pico. As far as I can tell, that's not possible using the standard libraries. This was far from easy, so I'll explain some of the issues I had and cover some of the things I had used to debug both devices using the UART on the Raspberry Pi Pico and the USB connection on the Arduino. The end result is a situation where the Raspberry Pi, the Arduino and the Pico are all on the same I2C bus. The Raspberry Pi will take a value from the Pico and then separately from the Arduino. I'll be implementing a variation of my voltmeter project for this, but it's not intended as a real project, but more as a way to show how I could incorporate I2C in a project. I'm also planning to use I2C in another project very soon, so this is going to be the theory so that the future video can concentrate on the more practical aspects. So if you'd like to see my future video, please subscribe to my channel and you'll get notified about those in future. As I usually do, I've split this video into chapters, so if you want to jump ahead to a particular example, then you can do so through the timeline or through the description. I'm going to start by looking at I2C and how it can be used for communicating between devices. I2C is an abbreviation of Integrated Circuit. You'll also see it written and referred to as I2C. This is particularly popular in code examples or online where creating the superscript for the 2 is not so convenient. It was created by Philips Semiconductor as a way to communicate between integrated circuits needing minimal connections. It is a common protocol often used for connecting devices to a computer or a microcontroller. I've already covered UART serial and SPI in other videos, so I'll start by comparing it with those. It's not possible to fully compare with just a few bullet points, but I'll cover a few of the important ones. I'm going to be looking at a specific focus at the instance where we're creating a connection between a computer and a microcontroller. The first obvious difference is that the UART is designed for only one pair of devices to communicate, whereas both the I2C and SPI support multiple devices using a single bus. This can be a limitation for UART if you want to connect to multiple devices. Next, we can look at the number of wires needed. These exclude the ground, which is also needed for all the protocols. Both I2C and UART use 2 wires, although in the case of UART that is for only one pair of devices, whereas the other protocols can be used for multiple devices. For SPI, I've put 4 wires plus. That's because whilst there are 4 wires going to each of the peripheral devices, the controller needs an additional enable output pin for each additional device, so the controller end needs to use more. The I2C protocol uses a unique address for each device. This has some pros and cons in terms of address conflicts, which will be explained later. The UART is a point-to-point connection, so that makes it simple in terms of which device to connect to. SPI uses an enable pin. Finally, looking at the speed. Although I've intentionally left this to the bottom, as in the projects where I use serial communications, it's rarely a limiting factor, but it could be for other projects. UART is the slowest, typically up to 115 kilobits per second. I2C is typically around 400 kilobits per second, whereas SPI can be around 12 megabits per second. Note, however, that these values can vary a lot depending upon the particular device, distance and cabling. The one thing I haven't listed is distance between the devices. This is because it can depend upon a number of different factors, and for most intended purposes of around 10 meters or less, then all 3 can be used. For UART and SPI, then 10 meters or more is fairly typical, whereas for I2C the official guidance is about 2 meters. However, with I2C it should be possible to achieve distance of 10 meters by running at a lower speed. The final thing I'll mention at this point is that the choice between SPI and I2C may also depend upon what other devices you want to connect to. Although many devices are available in both I2C and SPI variants, if you're already using a particular device, then you may want to use the same protocol to reduce the number of connections needed. So which protocol is best? Well, it really depends upon your needs. You should look at the different pros and cons for each project that you do. I'm going to use a specific example here, but only so I can nominate a winner. If I use a different project, I may choose a different technology. The project I have in mind is a model railway project. I'd like to have a single Raspberry Pi which can control various different peripherals, with things such as house lights, traffic lights, etc. The peripherals I'm wanting to control are going to use Arduino-like circuits built around a custom PCB. So the first elimination is clear. There's only one UART on the Raspberry Pi GPIO, whereas I want to be able to control multiple peripherals. The UART isn't really suitable, so that goes in third. Both SPI and I2C are suitable contenders for the top spot. My decision comes down to available pins, as I'd like to be able to control as many devices as possible from a single IC, in this case the ATmega 328P. The ATmega 328P has 14 digital pins, but I'll discount the serial UART pins as they're needed if I want to reprogram the chip. Although it is possible to use them as an output, it's not so convenient. So that's down to 12 pins. Using 4 for SPI leaves only 8 digital pins. I2C uses only 2 ports compared to 4 for SPI. In addition, so that it doesn't use the digital ports, instead using the analog inputs, although they can be configured as digital outputs anyway. Based on using only 2 pins versus 4 pins makes I2C the winner. The fact is, it's really too close to call. You could just as easily use I2C or SPI, but the crucial thing is that I've already created a video on SPI and not on I2C, so this gives me a reason to use I2C. The project is real though, and I probably will use I2C, just because it uses less wires. Even though the result is close, it's worth going through an evaluation exercise for each project rather than just going with what you've used before. Hopefully I'll be creating this project over the next few weeks. As I've said, the project I'm considering is based on a processor in the Arduino, the ATmega 328P. There are only 6 analog in ports on the ATmega 328P, as you can see in the top right of this diagram. If you do need more than 4 analog inputs, then SPI may have been a better choice. But in my experience, it's not often that you use all those anyway. Before we move on, I'd like to dispel a possible misunderstanding. Just because I2C uses the pins that are known as analog pins does not mean that I2C is an analog signal. It's a digital signal driven using an open drain. It's just that the internal I2C circuitry is connected to the same pins that are used for 2 of the analog to digital converter inputs. The mode of the pin can be changed through your code on the Arduino. I'm also wanting to use this with the Raspberry Pi Pico and perhaps other microcontrollers, so that I can use those peripherals without needing to create my own custom PCB board. The same advantage of I2C applies for any microcontroller, as it uses less pins compared with SPI. Here I'll show how devices are connected to the I2C bus. There are different terminologies that can be used. I'm going to be using controller to indicate which device is controlling the bus, and peripheral to refer to the other devices. You may also see other sites which refer to these as master and slave, and you may see those used in the code as well. In I2C, then you can have multiple controllers. The same device can switch between being a controller and in peripheral mode. To keep this simple, I'm going to show you just one controller and 2 peripherals. This will keep it fairly simple to follow, and we'll cover what we need to know when implementing it. If you want to understand how multiple controllers work, then I suggest you read the I2C specification. First, we need a data line, which is known as SDA for serial data. This goes from SDA on the controller to any of the peripherals. The controller sends information to say when it's going to use this line, or when each peripheral can use the line. The second wire is known as SCL, which is the serial clock signal. This is needed to ensure that all the device's clocks are in sync for sending and receiving information. There also needs to be a pull-up resistor for both the data and clock lines. This is because the I2C connections are open drain connections. I've explained this in more details in my earlier video on MOSFET logic level shift circuits. This should normally be external, connecting to the positive supply voltage. Some devices already have built-in pull-up resistors, although that can introduce problems with multiple devices, which I'll explain later. To add a second peripheral, then it just needs the additional device to be connected to the same bus. To identify which peripheral the controller is communicating with, then each device has a unique address. This unique address is used even when there's only one peripheral connected. But now it's important to ensure that you don't have two devices with the same address. The controller does not need an address, as that is the one directing the communications. As I said, you'll normally need to use pull-up resistors, which should be external. Some devices may include them, which can sometimes work. The internal pull-ups on a microcontroller are normally too weak to be reliable for I2C. Typical values of pull-ups are between about 2 kiloohms and 5 kiloohms. For short connections, then you can use a higher values, perhaps using just the standard 10 kiloohm on a level shifter. But for longer distances, then you may need to use lower values. When you create a bus, then you need one pair of resistors, one for the data and one for the clock line. If you have devices that run at different voltages, such as a Raspberry Pi at 3.3 volts and an Arduino at 5 volts, then it's important that you connect these to the lower voltage. Connecting to a 5 volt supply could cause permanent damage to a 3.3 volt device. In some circumstances, you may need to use level shifters. It may be a good idea anyway, just in case a 5 volt device does include a pull-up resistor. You don't need to add additional resistors when you add more devices, as long as there is one pair of resistors. An exception is if you do use a level shifter, when you need to ensure there's a pull-up for both sides of the level shifter. The example I used in my earlier video includes a 10 kiloohm pull-up resistor anyway, but you may want to add a smaller resistor. Watch out for devices which include pull-up resistors on the PCB. First, there is a risk that they may add 5 volts to a 3.3 volt device, and these usually have high resistance pull-up resistors. You may still need to use a lower resistance if you need to use it on a longer run. Also, if you have a lot of devices, then you may end up with too low a value, as effectively every pull-up is in parallel. If you don't add your own external resistance, then you can probably install about 7 devices with their internal pull-ups before the resistance becomes a problem. The address for I2C is normally 7 bits long. The standard does allow for 10 bits, but that is rare. So using the 7 bits would allow for digits 0 to 128, but some are reserved. The address is normally in hex, so that's what I'll be using, and the valid range is from 8 to hex 77. There are different ways that the address can be defined, so I'm going to list these in order of the most flexible. Addresses can be defined in software. This is normally the best, as it means that you can potentially set any address. This is what we'll be doing on the Arduino and Pico. The only negative thing is that the way I implement it means that you'll have to recompile the code to change the address. Although it does mean that you don't have to lose any of the pins of the processor to code the address with. Some devices may allow you to change the address using a dip switch or a jumper. Usually these will have a reduced range of addresses that can be used, but by selecting appropriate values you can get multiple devices to work correctly. Next is that some PCBs have small pads that can be soldered to, or where tracks can be cut with a knife. These offer a small amount of flexibility. It's okay when you only intend to use the PCB in a single setup, but isn't so convenient if you need to change the address. Finally, some devices have a fixed address which cannot be changed. This means you cannot use more than one of those devices with that address on the bus. There are some ways around it. Some have an enable pin which could be polled, or you could get an I2C multiplexer, but really these shouldn't exist at all, because you should always be able to change the address of a device somehow. That's the theory out of the way. Let's look at some practical examples. The first example I'll use is the Raspberry Pi Pico. I was hoping to use this in my earlier video using MicroPython, but unfortunately MicroPython does not currently support the Pico as a peripheral device. Whilst it would be possible to use this to communicate with the Raspberry Pi computer using the Pico as the controller and the Raspberry Pi as a peripheral, that would mean I could only ever use one Pico, unless I was using multiple controllers. So in this video I'll be using C on the Pico. I'll still be using Python on the Raspberry Pi, as that allows me to create a simple GUI using Pygame 0, although this introduces a bit of a problem with incompatible implementations. The Python library I used is known as the SM bus, which implements System Management Bus. This is based upon I2C, but uses a different messaging. They do work together, but I wasn't able to send multiple data blocks, and I did implement a little trick to be able to send data 16 bits at a time. The physical wiring is straightforward. The Pico is a 3.3 volt device, so it's easy to physically interface with the Raspberry Pi computer. I used I2C 1 on the Raspberry Pi, which is the I2C that is user accessible on the GPIO. This is on GPIO 2 and 3, which are physical pins 3 and 5. On the Pico there's a choice of two I2C devices. Between them they could be mapped to virtually any pair of GPIO ports. I used I2C 1, which is assigned to GP2 and GP3. On the physical pins this is 4 and 5. They also need to have their grounds connected together. I included physical 4.7 kiloohm pull-up resistors to the 3.3 volt output on the Pico. You could do this on either the Pico or the Raspberry Pi, but ensure that you use an output that is labelled as 3.3 volts out. Do not connect to any of the pins which are at 5 volts, either on the Raspberry Pi or the VSys or VBus on the Pico. Doing so could damage the Pico and the Raspberry Pi. For debugging purposes, I also connected the UARTs for the Raspberry Pi and the Pico. There are also debugging pins that could be used on the Pico, but I've already implemented the UART code and so was able to reuse this. This is explained in my earlier video on the voltmeter project, which I'll link to in the description. Let's take a look at the code. There's quite a bit of code which is for the UART debug and the analog to digital converter, which I've already covered in a previous video. So I'll be skipping over those quite quickly, and if you want to get the full details, then if you take a look at that previous video you'll be able to see that there. I'm going to mainly concentrate on the I2C part of the code. And starting with this, so this is the hardware I2C.h file. So that's the library file that includes the I2C code. And remember that needs to go into the cmakelist.txt file as well. This is for the UART for the debugging. So the next thing is the address. So this is the peripheral address for this Pico, and I've put 0x3e, and then the analog to digital converter. The one change I've made here is to turn this into millivolts. Previously this was in volts, 3.3 volts as you can see there, and by multiplying it by 1000 we'll get that in millivolts, and that way we can use it as an integer value which is easy to send. Whereas before I was sending that as a string. So set up the analog to digital converter. I've only used the one pin this time, which is pin 26, analog 0. Set up the UART for the debugging. The one bit I've dropped from this is that I've taken out all the code that's for the interrupt handling that was on before, because we're only going one way. We're only going from the Pico to the Raspberry Pi. We don't need to be able to handle any traffic in the other direction. So this is really the section we're interested in. This is the I2C setup. We're initializing using I2C 1, so that's the number 1 of the modules, setting it, and it refers to here as slave mode. That's the same as peripheral mode. It's a different terminology. I prefer to refer to these as peripherals, but they've used that. And this is where the address is defined. Then these are the functions. The set function is used to determine what pin these have been put on. So this is saying that GPIO pin 2 will be used for the I2C. And then it's got 2 pull-ups. So these are the pull-up resistors. I've actually used external pull-ups on this, so these aren't required. And these are quite high value pull-up resistors inside the integrated circuit anyway, so may work for a short distance if you've got them quite close together, but really you're better off with the external ones anyway. A bit of a debug message on the UART, set up some variables, and then all the handling really is in this while loop. We use I2C get read available to see is there anything ready to be read, and if so then it will read. It reads 3 bytes. Now the code you're going to see in a minute on the Python on the Raspberry Pi uses a slightly different protocol. It uses SM bus, and that sends the data as 3 bytes. I'll go into more detail in there, but basically what I'm doing, I'm taking the first byte, which is received as the lower 8 bits of an integer number, the second byte as the higher 8 bits, and then the third byte is just 0. So we'll ignore that. And I've just got a debug message there that I've actually removed, so I was showing the individual bytes, but this is the debug message, how we add the 2 together. So the first byte is there and the second byte is shifted by 8 bits. Puts that out on the UART. So that's how the receive part works, and that's purely here just so that you can see how you can send data to the Pico. And then this is the bit which is going to read the analog to digital converter and send that data on the I2C to the Raspberry Pi. So it just uses the standard analog to digital read, multiplies by a conversion factor. So now we've got an integer value. Note it's effectively, this is like using the floor command. It's rounded down, just dropping anything below the fraction part, but as that's fractions of millivolts, that's really irrelevant. We don't need that level of detail here anyway, so that's fine. Splitting it into 2 bytes here using a bit mask, so just to get the bottom 8 bits, and then shifting to the right to get the top 8 bits as a single byte. Puts that on the UART just so that we can see what's being sent, and then it uses the I2C write raw blocking and sends that as the data here, sends us 2 bytes. Now just go on both these, there's different functions available for the I2C code. In this case I'm using the raw commands. You see the word raw, and that means it's being used as the peripheral device and it's not looking for an address. It's just whatever comes into it, in the case of the read, and when you're writing out, it's just writing it out to the bus. It's not addressing it to another peripheral device. And that's the code for the Pico side, so that's compiled and then pushed out to the Pico. So now I'm going to look at the Python code which runs on the Raspberry Pi. So the reason I was using the code before in my previous version is because I wanted to be able to use a graphical user interface with this. I'm not implementing that here, but that's the same theory, is that I can then use that. And also I think Python is quite easy to understand and quite easy to write, so it's quite easy to get into. one of the issues here is that the I2C implementation of Python is through the module SMBus. SMBus is system management bus, and it's actually a variant of I2C. So it uses the same physical layer protocols as SMBus, although there's some little differences in the voltage and things like that. But essentially, it's a variant of I2C. And that means it behaves a little bit differently. So we have to use certain functions to be able to get these to talk. So I did a lot of playing around, really, rather than it being systematic. You couldn't really tell which functions were going to work. I just plugged them in and used the debug until I got something working. So just explain how these work then. So the address here is the address of the peripheral. The Raspberry Pi here is the controller, so it doesn't have an address, it just sends out the commands to the peripherals. Creates the bus, and then everything else is in this loop. I is going to be the value I'm going to send to the Pico. That was the value it just received and then squirted out to the UART. Doesn't matter what this value is. I made it 1000 because I wanted it to use the full range of the integer. If it was less than 256, then you wouldn't get to test the higher bits. So that's why I started at 1000. A bit debugging to let you know what's happening, and then it does a write to the I2C block data. Now this is this function uses the address to send it to, then it uses a command and then a list for the data. And when you're just using this on Python and talking to another SMBus device, you can set this command and then you can put multiple bytes of data in this list. However, when I tried that, I wasn't able to get to do it. What happens though is that the Pico can receive both these bytes. If I just put one byte in this list then and use that byte as well, then effectively we receive 2 bytes per thing. It doesn't matter whether that's an address or a value. So what it's doing is sending the lower part by masking it with FF just to get the lower 8 bits, and the higher part by shifting it 8 bits. And you notice the square brackets is to create this as a list of one object, because if you don't do that then it doesn't work. And also I wasn't able to get it to send multiple blocks of data, it would just fail to send it. But using it that way it works. You can send one 16-bit value at a time, which is an integer. Then read inside, similar sort of thing. We're using this read I2C block data, and in this case we're telling it how many bytes to receive, and it's going to read 2 bytes. Again, that can be used as an address, as a command when using other SMBus devices, but in our case it just means we're going to try and read 2 bytes, and it stores them in RX bytes, and I'm just turning these back into a 16-bit value by adding the byte 0 as the lower 8 bits and then byte 1 shifting it 8 bits to get the higher value, add them together, and then that's our value. So that's the Python code, and now we can just give a quick demonstration of this working. So I've set up UART debugging so I can use it minicom on here. I'll use the options -B for baud rate 115200, -O to force it, and the device that we've got it connected to is the serial port 0 on the Raspberry Pi. So again, I've explained that in my previous video if you want to see about that in more detail. We're now connected to the Pico for debugging, but that's not I2C, that's just the UART. And this is the one that is going to run the I2C and talk to the Pico. And as you can see, it's sending the data. So this is the value being written, so writing data 1009, 1010, and here it is on the Pico, that value there. And then transmitting wise, it's sending this value, which is 1835, 44-ish, which is millivolts, so that's 1.8 volts. And it's showing you how it's split into the 2 bytes that it's sending there. And we can make sure that that corresponds with here, and as you can see, these are the 2 bytes being received, and that's the value 1842 millivolts. And I can actually adjust that. I've got a variable resistor on, and if I just turn this slightly, then you'll see that value go up. There we go, so we're into the 2 volts region here, so we're talking about 2157, so around that. So it's fluctuating because this is millivolts. There's a slight change. Essentially, so what we've got here is we've got this Python program writing data to the Pico that you can see here, and then again this is the Raspberry Pi, so this is asking to read the value from the Pico, and the Pico is responding with this value here, which is the voltage, and we can see that that's being received successfully here. I won't be creating a project for the Arduino example. Instead, I'm just going to be creating a simple demonstration to show how it works. As with the Pico, I'll be using C on the Arduino, this time using the wire library. For the Arduino, this will work using event handlers rather than having a loop to keep checking for requests. It's a different method which has its own pros and cons. Something to be careful about is the voltage difference between the Raspberry Pi and the Arduino. Some models of the Arduino, such as the Uno and Leonardo, work at 5 volts, whereas the Maker series are 3.3 volts. The Raspberry Pi uses 3.3 volts. If you connect 5 volts to the Raspberry Pi, then that could damage it. It's possible to position the pull-up resistors on the 3.3 volt side, and then that should work for both devices. However, the concern is that if the pin used on the Arduino was activated as a normal output, or pull-up resistors were enabled, then that could damage the Raspberry Pi. I therefore recommend using a logic level converter, such as this one from Adafruit. I've already created a video explaining how they work. This will need pull-up resistors for both sides of the level shifter. Here's the wiring details. The Raspberry Pi side is the same as before. The Arduino uses analog port A4 for the serial data connection and analog port A5 for the clock. The Arduino can easily use the USB connection for debugging, so there's no additional connections needed for that. So now I'm going to show the code for the Arduino, which is written in C. I'm not going to be using this like as a practical example in the same way as the other one could be used as a voltmeter and it's sending a value. This is purely as a demonstration, so I'm just going to be sending static value from the Arduino to the console so that we can debug this and see it working. For the Arduino, then we're going to be using event handlers instead of the looped code, and this has got some pros and cons. It's going to actually in some ways make this a little bit easier. and we'll see how this works. The Arduino is set up to use the USB connection for debugging, so we're going to use that instead of having set up all the UART separately. They'll just go over the UART, which is built into the Arduino and communicates with the USB. Could use Minicom, but I'll be using a console here, which is part of the IDE for the Arduino IDE. So I'll just go through the code. So the library that's used here is wire.h, which is a library for I2C for the Arduino. You'll see that I've defined the address as being different from the other one. So the other one was 0x3e, this one's 0x3f. There's only one number up, but that will mean that these are unique if I go on to put them onto the same bus later. I've just set a value here to send, and it's just a 1, 2, 3, 4. I've just set that as. Now there's one of the things, the ways that this works is it's only going to be able to send the data 1 byte at a time. I'm wanting to send a 16-bit integer number as I did before, so I'm going to have to split that into a lower byte and an upper byte, and I need to keep track of whether I've sent the low byte or not, so that's what this variable is going to do. The setup is basically 3 lines, so saying join the I2C bus using that address, and then here's the interrupt handlers. When you get a request, then call the request event. When you get a received data, as in data is pushed to you, then use the receive event function. This is the debugging code. As you see, it's quite straightforward. It's just one, basically said just set up a serial connection, and then it's sending a single string to say that the device is starting, and then we'll be able to just use this using the serial.println later on. There's a loop here which is just doing nothing effectively. It's a delay, but this would allow you to put your own code in here, which could be running separately to the events. So there's the events are called, then it will handle the event, and then just carry on running this loop. And then everything else is inside these event handlers effectively. So if we receive an event, and this is that some data is being sent from the computer, the controller, to this Arduino as a peripheral device, it will tell you the bytes received. If it's less than 2, then ignore that. If you get, for instance, ones that just send 0 bytes, they are used as part of the I2C detect to detect devices on the bus. So it means we don't need to return anything. It's only when we get the 2 bytes requested, which is what we know we need to send. So it's only when we get the 2 bytes being received, which is what we're expecting to receive. Just set up somewhere to store that, and then as long as there's data available, store that inside this array here using the wire.read. And then, as we did before, we're taking the first byte as our lower 8 bits and the second byte 1 as the upper 8 bits, and just shifting that along, adding them together, printing it out onto the serial UART, and we'll be able to see that on here. The request event would actually be really straightforward, except for this aspect of it being only requesting 1 byte at a time. So when it's asked, send a byte. If it's the first time it asks, the lower cent is set to false, and it sends the lower byte of the integer value just by ANDing it with the bit mask for the lower bits. If that's already been sent and it's called again, then it knows it needs to send the upper 8 bits, and it's done by shifting the value. And then whatever it is, it sends that down the wire. And that's it. So it's actually quite a bit simpler, I think, in some ways for the Arduino. A bit less setting up and things like that. And we can see that in action. So now look at the Python code that we're going to use to test this, and you'll see in many ways it's similar to the one we did before. We're still using that same write I2C block, and all this is pretty much the same. Where we are different is the reading data. This is the command that we used before, and I couldn't get that to work with the Arduino. So what works with the Arduino doesn't work with the Pico and vice versa. Instead, we use the bus read byte, and this is just a more basic, just read 1 byte of data and save it here. And likewise, we call it twice. First one is the lower byte, and the second one is the upper 8 bits, and we can just print that as a value. And so we put it so that you can see Python code on the right and the console on the left, and we can run that, and hopefully, yeah, so it's writing data is incrementing 1000, 1001, 1002, you can see that 1010, 1010, and remember we sent this, it's always sending the same value, 1, 2, 3, 4, so I've not got it shown on here, but we always know this value is 1, 2, 3, 4. If you change that in the code, it will work, but for this, just get this nice and simple. And that just demonstrates how we can talk to the Arduino using the I2C bus. So now I've connected both the Arduino and the Pico to the same bus. Remember, they've got their separate addresses. The Pico's on 0x3e and the Arduino's on 0x3f, and that's how we're going to differentiate between the two. And basically what I've done is copy and pasted both sets of code into the same program. I'm going to run the Pico first, then the Arduino, and the only thing I've really changed is the address. Instead of referring to P address for the Pico and A address for the Arduino. There's obviously much better ways of writing this and keeping the code clean, but just for this demonstration, literally all I've done is copied the two into the one program, and just to illustrate how multiple devices can sit on the same bus. I'm going to run this on the command line just because there's big chunks between the lines, it's easy to see this way. And it's just C test times 2. And when we see this, we're going to see it running one, pause for a second, running the other. So it's only pausing for a second, so it's just going to jump quite quickly. And writing data, we don't have the console to see that's definitely been received, but we know it is because we've already seen that code work, and we've not done anything to the Pico or Arduino now since the previous example. And we can see that we're always getting 1, 2, 3, 4 back from the Arduino, and we're getting the value of the analog to digital back from the Pico. And there we are, multiple devices talking on the same bus. So using those same 2 pins, SDA and SCLK, the data and the clock, and talking to multiple devices. And we can add lots and lots more devices here. It's not limited to two. We can have multiple Picos, multiple Arduinos, and we can have other devices as well. In this video, I've shown how you can connect multiple devices using the I2C bus. This has been tested with the Raspberry Pi running Python and a Pico and an Arduino, both running C code. You can also add many other devices to the I2C bus. In the past, I've used it to send data to displays for an LCD display and other peripherals. Unfortunately, it does not look like MicroPython on the Pico currently supports this mode, although perhaps that may be added in the future. The one downside so far is that I had to use different commands to collect data from the Pico as I did from the Arduino. This was through trial and error that I managed to get this working. But if you know of a better way, then please let me know in the comments, and I may be able to use that in a future project. I hope you've found this useful. I'm looking at creating a new project using this in future, so please subscribe to my channel if you haven't already, so you can see that when it's available. Thanks for watching, and I hope to see you again in a future video.